All right, so here's a quick review of everything you should know. The formula for the pendulum is given right here, and there's a couple things to notice about this formula. First of all, the period is proportional to the square root of the length. So the first thing you need to know is that the period varies like the square root of the length, which means that if the length gets 4 times bigger, if this length of the pendulum gets 4 times bigger, the period gets the square root of 4 times bigger, or 2 times bigger. Okay, so increasing L makes T get bigger, but it's not linear. Okay, if we make the length of the pendulum 9 times bigger, the period would get the square root of 9, or 3 times bigger. All right, so that's the first thing you need to know. The second thing you need to know is that the period is inversely proportional to 1 over the square root of the gravitational constant, meaning that as the gravitational constant gets bigger, then the period gets smaller. They're inversely related, okay? We can represent both of these relationships with graphs. So if I have a graph and I graph the period and the length, the period is proportional to the square root of the length, so the graph will look something like that. On the other hand, if I ask how does the period depend on the gravitational constant, then if I'm looking at the gravitational constant g, as g gets bigger, the period gets smaller. The graph would look something like that. The other thing to notice is that in this equation here, there is no mass. It does not depend on the mass. So if we asked, how does the period depend on the mass, then it would look like this. It's a horizontal line. The period does not depend on the mass. It also doesn't depend on the angle at which it swings. Okay? So in general, the bigger the length is, the bigger the period is. Now remember, the frequency is 1 over the period. So if the period here gets big, the frequency gets small. And if the period gets small, the frequency gets big. They're inversely related. So how the period of a pendulum depends on its length, L. A big length is a big period. But if we ask how does the frequency depend on the length, if you have a big length, you have a big period, and a big period means a small frequency. So the biggest length has the smallest frequency, and the smallest length has the biggest frequency for a pendulum. Okay? All right, moving on, we have a mass on a spring. And the equation for a mass on a spring is given by this right here. It depends on the mass. So for a mass on a spring, it depends on the mass, and it depends on the spring constant. And remember, the spring constant is a measure of how strong the spring is. The bigger K is, the stronger or the stiffer the spring is, the more force it takes to stretch it. So in this case here, we would say that the period is proportional to the square root of the mass. That means that as the mass gets bigger, the period gets bigger. If the mass gets 4 times bigger, the period gets the square root of 4, or 2 times bigger. If the mass got 100 times bigger, the square root of 100 is 10. The period would get 10 times bigger. That's what that means. We can represent that on a graph. So on a graph, it would look something like this. Here's my graph. If I were plotting the period and the mass, it's proportional to the square root of the mass. So it would look something like that. Okay? The other thing is that the period is inversely proportional to the spring constant. So it looks like this. So as the spring constant itself gets bigger, because it's in the denominator, T gets smaller. And so on a graph, that would look something like this. If we're asking how does the period depend on the spring constant, it is inversely related. It goes down. Okay? Most things act like masses on springs, things like tuning forks or guitar strings, or any kind of vibrating string acts like a mass on a spring. Okay? All right. The next thing we talked about was the wave equation. The important thing about the wave equation is that the velocity of the wave is determined by the media alone. It does not depend on the frequency or the wavelength. If you make the frequency bigger, that makes the wavelength smaller. But it does not change the velocity. The velocity is independent of the source that creates the waves. It depends only on the media. The two velocities you need to know are the velocity of light, which is 3.0 times 10 to the 8th, and that's in your toolbox, and the velocity of sound, which is 341 meters per second. Okay? So there's an inverse relationship between the wavelength and the frequency, and that's given by the wave equation. The next thing we talked about was intensity, and there's two equations that allow us to calculate the intensity of the sound wave. First of all, the intensity of a sound wave is determined by the power of the source. The power of the source is the energy produced per second. It's in watts. However, that energy is spread out over some area, and that area is given by 4 pi r squared, and so the intensity is given by P over 4 pi r squared. So that's how we calculate the intensity, but that's not how we represent the sound level because our ears don't hear things in a way that's proportional to the intensity. So we calculate the sound level using this equation. It's the decibel equation. This right here is this thing right here. It's the intensity of the sound wave. In the denominator here, we have I0. It's a constant. It never, ever changes. It's going to be that all your whole life long. So to calculate the sound level, you take 10 times the log of the intensity divided by the reference, which is that value right there. Some important things to notice about the sound level. Every time the intensity, I, increases by a factor of 10, the decibel level increases by plus 10. So if the intensity gets 1,000 times bigger, then 1,000 is 10 times 10 times 10. And so the decibel level goes up 10 from there to there, and then it goes up 10 and then 10. So the decibel level would increase by 30. Okay? So every time it gets 10 times louder, you add 10 to the decibel level. And the same thing is when you decrease. Now, this equation here is kind of complicated, and so we gave you a shortcut. If you have to solve this equation for I, if your plan is to solve for I, the shortcut is that I can be written or found by taking I0 times 10 to the power of the sound level divided by 10. So the solution to this equation right here, the solution to that equation is this equation here, and you can put that in your toolbox and use it, okay? So you can calculate the intensity if you happen to know the decibel level, all right? The next thing we talked about was the Doppler effect. The Doppler effect comes about because when a source of waves is moving towards you, if I have a duck swimming towards me, the waves that it make bunch up in front of it. So if this is my duck and my duck is moving towards me, the waves it makes spreads out, but the duck is moving in this direction, the waves bunch up in front there, and the frequency is higher. So this is the frequency we observe, that we hear. This is the frequency that the waves are being created. This V right here and here are the velocity of the wave. Be careful. That's how fast the wave moves, and this is the velocity of the source. And of course, the sign depends on whether you're moving towards or away. If you're moving towards the object or the object's moving towards you, then you use the minus sign. If you're standing here and it's moving away from you, you use the plus sign. Okay? So that was the Doppler effect, and the Doppler effect works for all waves. It's not just sound waves. The very last thing we talked about was standing waves. So if you have a string and you stretch it between 2 points, and you cause a disturbance, there are many different vibrational modes. The first mode is called the first harmonic, and it's when you get 1/2 of a wave. There's also another frequency that will resonate or cause standing waves, and that's when you have a whole wave or 2/2 of a wave, and that's n equals 2. You could have 3/2 of a wave, that's n equals 3. You might have 4/2 of a wave, which is 2 whole waves. And that's n equals 4, and it goes on and on and on. So the equation, excuse me, that tells us the frequency of these waves is given by this. So the thing to remember here, L is the length of the string, how long the string is. V is the velocity. How fast do the waves travel back and forth on the string? And in general, this V is not 341. Okay? N is the harmonic number, so N is 1, 2, 3, 4, 5, or whatever. And you can calculate the frequencies of the harmonics. Of course, you can always use the wave equation if you have to. So once you know the frequency, the velocity of the wave is equal to the frequency times the wavelength. So once you find the frequency, you could find the wavelength, for example. This is what you get when you have waves on a string that's fixed on both ends. That's what this is about. You can also have resonance in air cavities. So if you have a column of air, like a pipe, and it's open on one end, then you can get a quarter of a wave resonating in there. You can get a 3/4 of a wave, or 5/4, or 7/4, or 9/4. In general, this is the equation that tells us the frequencies that will resonate. There's two things that are different about it. Since the velocity of the wave is the sound wave, this V here is 341. It's the velocity of sound in air. There's a 4 down here instead of a 2, so watch out for that. And the harmonics are only odd numbers. You can get 1, 3, or 5. There is no 2. Does not exist. Okay? So those have to be odd numbers. So that is a quick flying review of the unit. We also talked about resonance, so you'll have to understand what resonance is. But that gives you an idea of some of the things we're going to cover on this unit and on the test. All right?